All right. A few other announcements. Our SAC reps have been announced for Complexity and Michael. As I mentioned, there's also a transfer student representative. And so the Podstar is the transfer student representative. And then finally, as far as announcements, it's career fair season, so there's a lot of these going on. Just a few. There's Career Fest, September 19th, 23rd. There's a whole bunch of events going on. We're coming to be on campus and talking to students, wanting to talk to students. It's also the STEM Career Fair, September 27th. Now is really a great time for you all to be looking at or talking to companies not already. And ideally trying to line up some kind of internship for the summer. So you can already work someplace and want to continue. I'd say now's a great time to start trying to figure out internship for those. Start reaching out now. All right. Here's some more information on a few other career fair type events that may be of interest. All right. Any questions on announcements or material so far before we get started? All right. All right. This was a question last time, which I feel like I didn't give a very adequate answer to, which is why we include HF, even though we have no subcondition of the pipe wall. And I went and looked in our notes for internal flow chapters, and not really adequately addressed there either. So I want to discuss it now. So the question was, when we developed this form of the energy balance, we included, we previously said that the viscous work is 0 because no subcondition of walls. But when we developed this from the energy balance, we included this aged friction. And we said, or I said, that it's going to become really important when we start dealing with internal flows later in the text, chapter 6. But why? Like, where does this term come from? We get rid of the viscous work term. Where did this term come from? It didn't come from the viscous work. The explanation for that is that friction represents the fact that friction within the fluid itself. So if we have flows in a pipe traveling at different velocities across the cross section of the pipe, and that causes drag between the layers of the fluid itself. So that causes friction within the fluid itself, which locally increases the internal energy, and eventually results in heat transfer out of the fluid. Right? So that's friction generating heat within the fluid itself. And we should note this is not useful work. It's not work that we're getting out of the fluid. This is frictional work being lost, right? Frictional, this energy being lost through friction. So it's not useful work. The V dot B is still 0. But this effect is very important. You see in chapter 6, this effect is the dominant effect when we're talking about pipe networks. And it's going to be how we keep track of the flows of pipe networks. And so we lumped it into the heat term, right? So we lumped all of those effects of heat, of friction rather, into the heat term. And then we said we're going to ignore, I was not clear on this, but then we said we're going to ignore the rest of the heat transfer effect, right? Or other sources of heat transfer. And what we're left with is this heat friction that pops out of the heat term, not the viscous work.
Yeah. So why then, like, I've done some work with pipes that works for my job, and like different kinds of pipes have different like coefficients of friction where you like use it as kind of a K value. So they don't even like there's no condition of why we have different friction values for different kinds of pipes.
Yeah, so the question is, why do we get different friction values for different kinds of pipe? And this we already spent quite a bit of time on. I know graders spent quite a bit of time on this one, assuming that we're going to. But we'll see that for when we have turbulent flow within pipes, the roughness of the pipe walls, right? So like like basically like a texture. Imagine like a texture that I'm feeling here, right? The roughness or texture of the pipe walls has a very large impact on the friction that flow feels. If we're going to account for that, that's going to be one of the major parameters that you have to account for when we're analyzing pipe flow networks that you have.
But the friction isn't from the fluid to the pipe, but rather the fluid itself.
It's the fluid against itself, but it is influenced very strongly by what's going on. Right, because what's going on, what we'll see, so actually just the roadmap of where we're going, just maybe get a chance to stop it as well. We're about to go into, we're finishing up chapter 3, where we developed basic balance equations. In chapter 4, we're going to take those balance equations and we're going to turn them into differential equations. We're going to derive Navier-Stokes. It's not going to be a 5 minutes left in a class kind of derivation. It's going to take us a little bit longer than that. But we're going to derive Navier-Stokes in chapter 4. Chapter 5, we're going to talk about scaling. So we're talking about how we can simplify those equations in using non-dimensional parameters. So all the ideas like Reynolds number is a non-dimensional number, Mach number is non-dimensional. We're going to talk about that in a more rigorous way. And then in chapter 6, we're going to apply what we've learned to pipe flow networks. And we're going to see how we can use those tools that we've been building for a long time to understand what happens for flow within individual pipes and then eventually networks of pipes together. And we'll see that we can use the equations that we developed, for example, in chapter 4, to predict the velocity profile across the pipe, which is how the velocity of the pipe depends basically on the pipe walls. And from that, we're going to develop an expression for the CHI. Okay, so we're getting there. And along the way, we will talk about wall reference. But that's it. Okay. But I was not very clear about this last class. I wanted to clarify. Does this make some sense? Okay. So, but maybe the simplified version of this is that the frictional losses are not useful work. This would be useful work to get out. The frictional losses are not useful work. It's energy transfer to heat. So this term called out the okay. So back to Bernoulli. So yeah, and notice there is someone's keeping track of things being said. I'm just glad someone's paying attention. I'm glad someone's paying attention. But this, as I said it, I thought it was going on. So be careful with the Bernoulli equation. It's definitely very widely overused. Yeah, sometimes wildly overused. So look at the Bernoulli expression that's one coordinate is up on the top right of the slide. It doesn't have that HF term, right? The head velocity friction term. It doesn't have anything about energy being transferred into or out of the fluid that you have to worry about. So that's the simplicity of the Bernoulli. But you have to be careful because if, for example, you're studying a pipe flow network, as we'll see exhaustively in chapter 6, then if you just use the Bernoulli equation, you're going to be missing something really important. You'll be missing the head loss, which is actually the major driver of understanding what's going on in flow within pipes. So you have to be careful, right? The Bernoulli equation is very, very wide. And part of it, part of what makes it seductive, right, is that if you have, we'll see that when we have a pipe flow problem, you're going to be typically given a delta P, right? A change in pressure across some length of pipe. And you're going to be asked to find, you might be given a delta C, you might be given a change in height, or maybe that pipe is at some kind of angle. And you're going to be asked to find a velocity. And if you look at this equation, it has pressures, it has elevations, it has velocities. So people are often tricked into thinking, well, great, it has all of the variables that I need in it, and therefore I can use it in this context. And we'll see when we get to pipe flow analysis, that's definitely not true. You cannot use the Bernoulli expression for analyzing flow through pipe. So be careful. It's or flow through pipe and frictional loss. You cannot use Bernoulli. So be careful. It is very wildly overused. A note on this. So this expression is traditionally actually derived from the momentum balance, right? So we develop mass, the momentum, and energy. And in your textbook, after developing a momentum balance, actually go in and then derive Bernoulli from momentum. That's kind of a possible way of doing it. It's actually a lot harder, right? It's not something that's done in 5 minutes in the class. And I think it's a lot more clear to think of this as a result from energy, but if you want to be aware, you can also get the same place from momentum. Okay, so that's it. Notice widely overused. When applicable, like when you can use it, it's great off. Right. So when Bernoulli equation applies, it's fantastic. Very quick way to understand what's going on within a fluid system. So if you can use Bernoulli equation, you should. Just make sure you're using it correctly. And a note on knowing that we're going to talk a little bit about applicability of Bernoulli equation and cases where it does work. And we'll actually in the videos on Friday, we'll go through some examples of application of Bernoulli equation and when it does not hold in real life flows. But just a note about nomenclature, you'll sometimes see Bernoulli equation used to mean an energy balance. So sometimes you'll see an expression. This happens actually a lot in some in chemistry textbooks, chemistry specific fluid textbooks, where you kind of a general physics of fluids, fluid mechanics, general engineering fluid mechanics textbook. But sometimes in a chemistry specific fluid textbook, you'll see something called Bernoulli equation, or maybe the engineering Bernoulli equation, and it will be basically this, right? You'll see something like this referred to as Bernoulli. That's okay, right? But in this class, when we say Bernoulli equation, this is what we do. Okay. So I just want to be clear. And part of that is, I recognize that for many of you, you're not going to look at fluid mechanics for quite some time after this class. And then at some point, maybe a few years down the road, you're going to be asked to look at something involving fluids in your, in your professional life. Think that maybe you should use the Bernoulli equation, Google it or whatever it is by then, to figure out what Bernoulli equation is. If you go to Google, it'll send you to Wikipedia, and what Wikipedia calls the Bernoulli equation is this, right? What is generally referred to in most contexts as the Bernoulli equation is what I have on top, right? So that's why I want to be careful about what we call Bernoulli equation. So yes, sometimes you'll see Bernoulli with the correction factors or engineering Bernoulli, which is really just an energy. Okay. So we went through the derivation of Bernoulli equation from the energy balance, and there were a number of assumptions that we had to make in order to get to the Bernoulli equation, to that expression that's on the top right corner of this story. Right? We had to knock out a bunch of terms, and even actually getting to the form of the energy balance that we used to derive Bernoulli, we made a bunch of assumptions. All of those things place limitations on when we can apply this equation. Right? All of those things in totality have to be true in order for us to use this expression. We'll review them, but I just want you to get into groups and discuss, maybe dig back through your notes about what assumptions that we have, what are the assumptions that we have to make in order to use the Bernoulli equation. Okay, so please discuss groups of 2 to 3, and then we'll bring it up for the whole class. Right. All right, I think we're gonna call it there. All right, so I don't know, Lexi, our new SAC rep, what did you come up with? Well, there's a lot to choose from. So what? Steady, not necessarily constant velocity, but steady state, right? Our expression of Bernoulli requires a steady state. Not necessarily constant velocity, because remember we have a V1 and a V2, and they don't necessarily have to be equal, right? But steady state, definitely. All right, what else we have? Yep. Basically, nothing can happen except it moves from one place to another. Yes, that's basically true. But what are the things that can happen that we have to ignore to use Bernoulli? Just give me one example. Friction, right? So if there's friction, then Bernoulli does not apply, right? What else? Yeah, let's just go. Adiabatic, yep, right? So yeah, so we're not gonna have any, for example, we're not gonna have any heat transfer, right, into the fluid, right? So no heat, no friction. What else or do we have to have? Yeah. One-dimensional, right? Yeah, we derived, so one-dimensional, so uniform velocity. We also have one inlet, one outlet in our form, right? Yes. Does it have to be isothermal? In the form that we developed, yes, it has to be isothermal. Yep. What else? Yeah. Incompressible. Yeah, so we have an incompressible, right? We started with the incompressible assumption before we even got to the energy balance, right? That we then dropped terms out of to get Bernoulli. What else? Yeah. No work, right? So no shafts, no turbines within the control volume. Yeah. Yes. Yeah, no. Yes, it is. So I spent a lot of time on assumptions because discussing the assumptions and when it's not useful because it is very widely overused. But it is sometimes called the most powerful equation in fluid mechanics because it is useful. And one place it's really useful is, yeah, we want to understand flow within small pieces of equipment, right? Individual pieces of equipment, for example, where the frictional losses, maybe there is friction, but it's negligible, right? Then we can still apply Bernoulli. And for example, in the mantis shrimp, the pistol shrimp example, Bernoulli doesn't really strictly hold, right? There's a lot going on there, including compression of the fluid. But if we go just back to Bernoulli, if I can get there. We said that we can use Bernoulli to kind of understand why cavitation occurs, right? Because if we have velocity going up, then pressure goes down, right? And even though like this analysis wouldn't strictly hold, I mean, there's a lot of things going on in there. For example, it's not isothermal at all, but it still tells us that there's a trade-off in terms of energy within the fluid between velocity and pressure, and can help us build intuition to understand what's going on in those kinds of situations, right? So, so Bernoulli equation can help us build intuition about flows, right? So, for example, if the velocity is constant
and we raise the elevation, or a fluid by its flow raises its elevation, we'll see that we have to have the pressure go down. So it can help us to gain some intuition. It can also be useful for actual analysis in some situations. Yeah, for sure. Yeah, maybe I'm going too far on one side, but I've also seen it being used, being overused far too often. Yeah.
So I've heard that Bernoulli explain why. How true is that?
Yeah, so the question is, I'm repeating it for microphone. Can we use this to explain why airplanes fly? We can use it to understand why airplanes fly. I don't think it's a full explanation. We will actually, so aerodynamics is kind of beyond the scope of a fluid mechanics class, but I do think that by the end of a fluid mechanics class, you should have some idea of how airplanes work. So the last day of class, we will talk about aerodynamics based on everything that we've learned, and talk about why airplanes fly based on everything we've learned. And one of the explanations that you can use to understand how an airplane flies is Bernoulli equation. But basically, the short version is that an airplane wing is configured such that the velocity over the upper surface of the wing is higher than the velocity along the undersurface of the wing. And if we use the Bernoulli equation, right, if the velocity is higher, what happens to pressure? Pressure goes down, right? And if the velocity is lower, the pressure goes up. So the results of the flow around an airplane wing, right, higher velocity on the top, lower velocity on the bottom, is a lower pressure on top, which basically sucks the wing up, and a higher pressure on the bottom, which pushes the wing up. And the result is lift force, right? Now, that doesn't explain why there's a higher velocity on the top than on the bottom, which is why I'm saying it's not a full explanation of it, but it's a way to understand what's going on. Yeah, for sure. Okay. All right, so a list of our assumptions: steady, incompressible, frictionless, no heat, no work. Isothermal actually should be on here as well. Flow along a single streamline. So that basically meaning that we're looking at flow just in one region of the fluid. Actually, we do not have a full unit on irrotational flow, but we will discuss this in chapter 4. But irrotational basically implies no viscous. So if we have a flow situation where there is, where it's irrotational, basically meaning that there's no turning, no vorticity within the fluid, then we can apply Bernoulli in that region, implying, and this condition implies there's no viscous influence. So like here, we have flow that is very rotational, right? So there's a lot of vortices here, and so we would not be able to apply the Bernoulli expression. These are some examples from your text that give you a sense of both where we can use Bernoulli, right, where it's useful, and then the places where we cannot apply the Bernoulli expression. So, for example, if we have flow around, some kind of an aircraft model, in this case, it's showing it within a wind tunnel, the Bernoulli expression would be valid to analyze the flow outside of the model itself, right? So as we are some distance away from the model itself, and we'll see in chapter 7 when we talk about external flows. What we're really depicting here in this blue shaded region is called the boundary layer. It's basically the region where the viscous influence of the surface is felt. But away from that region, which is actually quite thin, it's very exaggerated here. Away from that region, we can actually apply the Bernoulli equation pretty well. But within the region that's close to the wall of the model or close to the wall of the wind tunnel, the Bernoulli equation would not apply. Same thing if we have some kind of a duct that's at relatively high speed, and we have some kind of a turbine here sitting within that duct, we'll often be able to use the Bernoulli equation, let's say upstream of where this blade is, right? This turbine blade. And then again, downstream But we would have to note that as we have this blade in here, we're going to have some work, some shaft work, entering the fluid or leaving the fluid. And so that's going to change the energy of the fluid. And so that would basically change the constant in our Bernoulli expression. But Bernoulli equation would help us explain what's going on here as well. Another example, so here is a fireplace, right? You might use the Bernoulli expression to understand what's going on. It's kind of the core of the flow, right? Again, away from the walls, entering into the fireplace. It would be invalid where we have, right, all that heat transfer going on. And then we would have a new constant because we have new energy within the fluid, but we'd be able to use Bernoulli equation on the way out. Okay. That makes sense? Okay. All right. And so related to this, there was a question in class at the end of class last time, which is when do I use which equation? And I just wanted to touch on this because we've developed a whole bunch of different expressions, right, in this chapter. And I know this is maybe the one thing that everyone wants to know most of all, right? Which equation do I use when? So I would say a general rule is start with the most general form that you're sure applies, and then simplify from there. And we'll go through an example. This is not exactly a question that was on a midterm, but it's related. It's kind of a mashup of question from two different midterms. So let's say we have this figure here at the right. We have some big reservoir filled with water. We're given the dimensions, the height and the depth and the areas. And we'll say that there's a pipe coming out, a really short pipe, and a really short pipe where we're going to be neglecting friction. And we're going to say that there's a valve located at the pipe outlet that's initially closed, right? So initially we close down some valve here before, and we're asked something about to analyze this system before we open up that valve. In this case, we want to know what is the absolute pressure at the pipe outlet with the valve closed, right? So we want to know the pressure right here, basically, right, with the valve closed. So one way to start this expression, start this problem rather, is to say, well, this looks kind of like an energy balance type problem, maybe. So we could start actually with an energy balance equation. And we have one inlet and one outlet. And so we can start with this form of the energy balance, right? Where we have, where we're relating the energy of the fluid at the top surface to the energy of the fluid at this pipe outlet, right? Or at this location right here. And then we'll say there's no heat, friction, pumps, or turbines within here. So we drop out these terms. We can also say that with the valve closed, the velocities are 0, right? And we'll end up with this expression, P over rho plus GZ at the top is equal to P over rho plus GZ at the outlet. And we can use this to find the pressure at that valve outlet. The other thing you could have done, which maybe some of you have recognized, what's another approach I could take to get to the same expression? What's that? Statics, right? So this is a statics problem. With the valve closed, there's no motion. So you could have also said this. You could have started with fluid statics. Delta P is minus rho G delta Z, and you get to the same exact expression. And you get the same answer. Okay. It's basically if you're in the situation of having to analyze this and you're not sure where to begin, but you know this applies, fine, start here, okay, and start canceling out terms. Or if you're confident that it's a fluid statics situation that you're analyzing, you can start here. Okay. Yeah.
If we actually do this question, you don't know that this is from the top of the valve. Is that a problem?
You know H, you know D, so you do know that distance. Oh. Yeah. Yeah. Tata. Situations where there's no velocity, but we can't use the statics equation. Not that I'm aware of, and not in this class. Yeah, yeah. But I mean, I understand when you're in an exam and you're trying to figure out what applies, and you're reaching for something, you can start here, right? And you get to the same place, okay? You know, so that's why I'm saying start with the most general form that you're sure of, right? So one question is, how do I know what I'm sure of? Well, you can start here, right? For this problem, you know, there's one inlet, one outlet. You can start here and drop out terms. So you get to the same, you get to the exact same answer, okay? In this case, you could have started with, you could have said, you know, maybe you could have assumed you're going to neglect friction, right, as well as heat and work, and started with Bernoulli, right? And anyway, you would get to the same place. Okay. Does that clarify that a little bit? Yeah. Okay. We'll talk about this a little bit more as we're, for example, preparing for the midterms, right? How to get started on problems. But another thing I want to draw your attention to is that there will often be more than one way to get to the answer for problems that I'm going to pose in this class. I'm not always looking for you to just find that right equation, right? So problems that I'm going to ask you are not generally about just choosing exactly that right form of the equation and then plugging in the given parameters. I'm really much more interested in seeing that you understand how to get to here, right? And whether you go this route or this route, right? You go the energy balance route or the statics route, I'm much more interested in seeing that you know how to get to here than I am in seeing you just pull out the right equation and plug in numbers, okay? So that's maybe a departure a little bit from other classes, okay? One other thing I want to draw your attention to while we're on the subject of exam questions, potential exam questions, and you'll see, I haven't decided exactly which one's going to be on your homework, but you'll see either the 2019 or 2021 problem that's like this on your homework this week. So in problems that come from your textbook, they're broken out typically by section, right? So in chapter 3, you have some problems on mass, some problems on momentum, some problems on energy. And oftentimes it'll be on like one specific form of mass, momentum, or energy balance. There's even headings in your textbook basically to tell you what equation you need to use if you have the text. You know, when I assign problem 3.52 or whatever. And so those problems are testing basically just one thing at a time. On exams, I will typically, like this problem here, starts with a setup like this. And then I ask several different questions about that setup that are testing different concepts. So in order to get through this whole problem, you have to apply different types of energy balances, right? Different types of balance equations, rather. Not different types of energy balances. Different types of balance equations, mass, momentum, energy, to understand what's going on in this system. And I try to guide you through that with like parts A through D or whatever it is in this problem. But you will, in general, have to know all of the things that we've learned in this class to approach these problems, okay? So that's another reason why I give you some of the old midterm problems on homework so that you're not surprised when you see that on the exams, okay? All right, any questions? Okay. So this wraps up our discussion in class of chapter 3. Homework, which will be assigned today, will cover this material through chapter 3. So you're gonna have a lot of practice on energy balance and Bernoulli, and maybe some momentum balance in your and mass in your homework for this week. Now, example problems, which we're kind of skipping, and ordinarily I'd spend some time on example problems, again, are up on YouTube, right? So I've recorded myself going through some example problems. And what I'd really like from you all is feedback on types of problems that you would like to see more examples of. And so if I get a few suggestions, that'll help guide me in choosing what types of problems that I'll upload this year, right, to add to that collection. So if you have any thoughts on things that you're having trouble with and would like to see me go through in more detail, then please let me know. Otherwise, I'm just going to choose, probably one each of mass, momentum, energy, Bernoulli. So the question is, on exams, will I ask you to derive equations or is it just numerical? So I'm not going to be asking you to derive fundamental laws, right? But I will sometimes ask for a symbolic answer, okay? So I guess I don't think of that as a derivation per se, but I will sometimes ask for a symbolic answer, okay? Okay, anything else? Also, again, since my emphasis is really on understanding where this all comes from and applying it properly, even if it has a numeric answer, I'm generally most interested in what you use to get there rather than the exact value that you got, right? So if you made an error plugging something into your calculator, that's penalized much less harshly than if you applied Bernoulli where it's definitely not applicable, right? Okay. Any other questions? All right. All right, so on to chapter 4. Oh man. Okay. Okay, so in chapter 4, we're going to be discussing distributions of velocity and pressure within fluids, right? So in chapter 3, we were primarily concerned with, so we were doing what we would call control volume analysis of fluids, right? So we said that, if we have flow through some region of space, we don't necessarily care about the details of what's going on within that region of space. We're just looking at the inlets and outlets, net applied forces, and we can use that to learn something about what's going on within that space. But now in chapter 4, we're going to be developing the tools to study really what's going on in detail when flow encounters objects and when we apply forces to flows. And so we're going to derive a series of equations that we can use to describe how velocity and pressure vary within a fluid flow, right? So we're going to get to the Navier-Stokes equations that we can use to describe an incompressible Newtonian fluid. So mass momentum for incompressible Newtonian fluid will give us the Navier-Stokes equations. And then we'll see, we're also going to develop a differential form of the energy balance, right? So a differential equation for energy balance that we're going to need later when we discuss compressible fluids, okay? And we're going to see that this single set of equations that we have, even just in the Navier-Stokes equations, this set of equations, which has been known for nearly 200 years, still the subject of active research. And this set of equations describes a huge range of fluid behaviors, right? So we can use the same set of equations to study what's going on here. So this is flow. We have flow again from left to right over a block. You can just kind of see the shadow of this block. And this is at very, very low speed. So we would call this creeping flow. We'll talk more about this. But and what we see is that at very, very low speed, we have the flow encountering the block, moving up around the block, and then symmetrically coming down on the opposite side with formation of these nice, neat little vortices on either side of the block. This behavior is described by the Navier-Stokes equations. But so is this. So this is flow again over a block from left to right at now higher speed. So we've turned up the velocity basically of the flow within our test system. And now we're seeing turbulence. This is turbulence that's occurring downstream of the block. This is definitely asymmetric, right? We do not see the same thing on the left as we do on the right. This has important implications for how we understand what's going on, the forces, for example, that are applied here. But this behavior, even though it's vastly different than this behavior, is described again by the same set of equations, the Navier-Stokes equations. Okay. So the tools that we're going to develop in this chapter are applicable to a wide range of different flows. And these expressions also form the basis of CFD, or computational fluid dynamics. typically in a CFD simulation, we're not using the balance equations that we developed in chapter 3, but these differential forms that we're going to be developing here in chapter 4. So these are 2 examples. This is a simulation of the airflow around a drone using CFD and the complex unsteady airflow around a drone. And then this comes from Professor Tony Saad of our department's simulations of the airflow in a Bravenel Hall. And this is done with CFD and essentially by solving the differential equations of fluid motion that we're going to be deriving in this unit. Now, there is you are going to have a project where you're just kind of dipping your toes into CFD that will happen later in this semester. And then another thing that we're going to do is we're going to spend some time discussing how we can simplify the equations that we're going to develop so we don't always need CFD in order to understand what's going on within a fluid. So that's where we're going, but we have maybe, as you might imagine, a bunch of math to do to get there, right? So the next couple classes are going to be a lot of derivation, right, to get to where we're going. And one of the first concepts that we're going to encounter is what's called Eulerian versus Lagrangian coordinates. So we look at, we're going to have some velocity field here. And this is bold V, vector V of bold R, vector R, comma T. A little bit washed out on the screen right now. But that vector velocity field, right, has 3 components. An X component, and we are often going to denote the X component of velocity as lowercase u. A Y component, we are often going to denote the Y component of velocity as lowercase v, which I know gets confusing. And as Z component, which we're often going to denote as lowercase w. Okay. And in general, these things now can vary within space and time, X, Y, Z, and T. So as we're developing our equations of fluid motion for velocity fields, and we'll also look at pressure fields and temperature fields later in compressible flow, there are 2 major approaches, basically named after Euler and Lagrange, called Eulerian and Lagrangian. The Eulerian approach, this is where we are, our frame of reference, right? The way in which we're viewing the flow that's occurring is stationary with respect to the flow. So if I have flow through this constriction here, this square here represents an Eulerian control volume. And we can see that it stays in the same place. So Eulerian analysis is fixed with respect to the flow. Sometimes we call this like the lab reference frame. Like if we imagine that we have this as an experiment in a lab, the lab is not moving relative to the surface of the earth. And so Eulerian control volume is fixed or has a fixed reference frame relative to the lab. This is kind of the natural way that we tend to think about flows, I think, right? And kind of naturally what we discussed in chapter 3, right? In chapter 3, we were considering Eulerian control volumes that were just fixed in space, right? The other approach is Lagrangian, and this is where we allow our control volume to move and even deform with the flow itself. So this is where we consider like a fluid particle as it's moving through the system. So this circle here represents a Lagrangian control volume. And we'll see that as time moves on, that Lagrangian control volume distorts and flows through the system. Yeah, ta-ta. So we're gonna have to assume constant volume or constant mass. We're typically gonna be assuming constant volume, but in compressible, we're gonna see that we're gonna have the same constant volume as constant mass. yeah, we have to hold something constant. So Lagrangian is everywhere moving with the flow. And this is kind of an unnatural way to think about it in terms of, sort of everyday experience. But what we'll see is that when we're trying to develop conservation laws, this Lagrangian perspective makes it a lot easier to develop those laws. So when we're trying to account, for example, for momentum within a fluid, if we use a Lagrangian control volume, it's a lot easier to account for all the forces on a little fluid particle as it's moving through the system than it is to try to account for all of those in an Eulerian system. So this little bit of weirdness will make our lives easier on the math side later on. We're generally, however, going to be solving problems in an Eulerian reference frame, right? Because again, we're generally going to want to analyze, flow within a fixed region of space or something, or flow within a fixed section of pipe, flow within a fixed section of a reactor vessel. So we're generally going to be solving problems with the Eulerian approach, even though we're going to derive conservation laws using Lagrangian approach. Okay. So let's look at an example of difference between Lagrangian and Eulerian, and it has to do with acceleration of a fluid particle. Right, so we have a piece of fluid that's moving through some flow system. We can write out the acceleration of that fluid particle as dv dt. Right, so just with ordinary dv dt. And again, remember that that's a vector velocity v, so it has three components, x, y, and z. And for each velocity component, we can then use the chain rule to say that the total derivative, so let's say we look at the x component. So the total derivative of the x component of the velocity with respect to time is the partial of u with respect to time plus partial u, partial x, partial t, partial u, partial y, partial t, partial u, partial z, partial z, partial t. Okay, so we have the total derivative written in terms of these partial derivatives. And now we recognize that the rate of change of x with respect to time for this fluid particle, that's just the velocity, right, in u. Rate of change of y is v, rate of change of z with respect to time is w, right? So I can now rewrite this term. So the total derivative of the x component of velocity with respect to time is partial u, partial t, plus u, partial x, v, partial u, partial y, w, partial u, partial z. Okay. All right. And on Friday after YouTube, we're going to pick up with that and use this to describe and discuss acceleration within a fluid particle and talk about it in Lagrangian and Eulerian terms. Okay. So next homework will be out today, covering chapter 3. And we'll pick up on this on Friday. Thank you all.